My name is Srinivasan Chandrasekharan. I'm a PhD student at the University of Arizona, and today I'm going to talk to you about a unique way to do power management for memory. I'm filling in the place of Mingsong who couldn't be here. This work was done under the guidance of Professor Gniady at the Computer Science Department. So why is memory power consumption interesting? People always seem to talk about dynamic scaling of frequency for CPU to perform power management, but nobody talks about memory. Memory power consumption as a percentage of the power consumption of the entire system has steadily increased, and therefore it is beneficial to understand memory usage and do power management for memory. In the last two graphs, I've shown the evolution and the increase of the number of memory banks on motherboards over the years. So from a simple dual-channel motherboard to now you have multiple channels on the motherboard that can fit up to 128 gigabytes of memory. Slowly, memory has started taking a pretty decent chunk of the power. Let's quickly talk about the current existing approaches to do power management. Current operating systems have a coarse power management technique. When memory is in high usage, memory is kept in high power state, and when the operating system recognizes that there is idle time, then the memory is switched to a lower power state. This is fairly common. Furthermore, a slight more granular approach is to pick a single power state for memory for the execution of a process, but it has trade-offs. If you keep memory in a higher power state, you get high performance, but then you don't save that much energy. If you keep the memory in a lower power state, you get hit with the transition delay for memory, and you may or may not save energy. Again, this is very fairly coarse. The next approach is PAVM, which is power-aware virtual memory. A paper written previously suggested that only ranks occupied by the current running process should remain in high power state, while all others can be kept in a lower power state. This works well in a single process environment, but with multiple cores and multiple processes running concurrently, there will be other ranks that will be powered up and therefore to a higher power state, and therefore reducing the energy savings as a whole. So we need a little bit more granularity. Let's quickly take a look at the memory demand for applications. We know that between different applications, you have different memory demand. So if you're using a word processor, I have a couple of applications here, but if you use a word processor, you see a different memory behavior. But when you use a video editing software, you see a different memory behavior. Also, the memory, whoa, sorry. Okay. We also know that the memory behavior within an application also is different. So, for example, let's take a look at GIMP. When you click or you rotate, a separate section of the code is executed, and therefore you have different memory access patterns. So let's we have this information now, so we can actually take a look at what we have from the application layer and see if these additional information can be used to do power management. So we see an opportunity to do finer energy savings mechanisms. First, so we did a quick test. We realized that there are short tasks that dominate interactive applications. So what are short tasks? Short tasks are small tasks that are less than 50 milliseconds. Second, we also see that some short tasks are able to tolerate a lower power state, but some longer tasks expose a higher latency to the user, which is not acceptable when you're using an interactive application. Therefore, we kind of need a dynamic mechanism for each process and each task. Furthermore, we also see that 93% of short tasks can be delayed for the user, and 58% of the longer tasks can be extended by another 50 milliseconds to get some energy savings. We call this the perception threshold. There is a perception threshold for a user. When they are using an application, they cannot just click fast enough, so they have to wait. So it's about 50 to 100 milliseconds. Therefore, there is opportunity to have energy savings, but we must remember that we can't just delay any task because we will cross this perception threshold, and therefore we need a dynamic mechanism. So our solution is called Interactive Aware Memory Energy Management. What it does is it dynamically captures user behavior. Performance is matched to the user interaction. It adapts when the user behavior changes, and there are no delays exposed to the user. So the benefits are energy savings is done during the process execution. We have negligible degradation in performance, and we don't have to do any modifications to the code. Now that I have talked a little bit about the background, this is how I've laid out my talk. I'll talk a little bit about the components in the overview section, the design considerations, the methodology of our paper, some results, and then I'll conclude my talk for questions. So we have three components in our system. The first is the user. He's the one who is he or she is the one who's generating tasks which result in memory activity. The user is expecting high performance, and the goal is not to expose any delays to the user. The second is the application, which generates the memory activity based on user interactions. We've already mentioned before that every application has a unique interface, and therefore unique interfaces will trigger different unique memory activity. So again, goal here is not to modify the application. And lastly, but not the least, memory. Our goal is to optimize performance and energy at the same time. So some of the things that we had to, one of the decisions that we had to make was we realized that for energy savings, we have to slow down execution, but we have to be very mindful to have an energy management system which is not noticeable to the user. So we take advantage of the perception threshold for the user, which is about 50 to 100 milliseconds delay, which is never noticeable to the user. So we can take that into consideration. We also have to be mindful that once you slow down the task, you should not exceed the perception threshold. So how do we go about capturing this user activity? So what we did was we added a monitoring layer between the application and the X server. It captures the mouse interactions and the keyboard interactions. And what we do is we assign a unique ID to every window element. We generate a unique ID for every window element. So any other actions that come for that particular window element UID triggers the same unique ID. So we are able to track it that way. Again, I keep repeating myself, but applications remain unmodified. This is very important for us. The next thing is how do we monitor memory activity for this particular task? So let's define what a task is formally now. What we call a task is any CPU and memory I/O resulting from user interaction. So when you click, there is a user interaction that you trigger, and you trigger some memory, and therefore that's considered to be a task. It begins with a user interaction and ends with idle time. So after the execution of the task, the CPU goes to the idle time. So we say that slice is supposed to be that slice is called the task. So how do we measure? We measure the task length using the timestamp counter. We measure the memory references using the performance counter, especially for the L3 last level cache miss performance counter. And now with this information and with the perception threshold, we can calculate the best power state for this particular task. But what we realize is that there is a big trade-off between power and delay, especially in DDR3, which has introduced two other states than DDR2. Here we classify the active standby and the active power down state as a higher energy, higher power states, while the others, self-refresh that we know about already, pre-charge slow and pre-charge fast, we consider as lower power states. So we have to be very mindful of which state we pick, because we ultimately do not want to expose any delays to the user. So the first thing we have to do is we have to correlate the memory references to each UID, which is the unique event ID. So we keep track of basic task history. We keep time, which is the weighted sum of all previous task lengths. We keep track of memory references, which is, again, weighted sum of all previous memory references, and count, which is the weighted count for all previous task instances. And we use the history updates, which is based on a aged alpha statistic, which allows us to adapt to new patterns of memory behavior and user interactions. So the next thing we have to do once we have this information, we can predict. So it's pretty straightforward. The UID comes into our daemon, and we check if for that particular UID, does a table entry exist. If a table entry does not exist, we quickly put the memory in high power state because we don't want to expose any delays, we don't want to mispredict. So we'd rather take that energy hit now. If the table entry is found, we predict using the task length and the number of memory references. We calculate all the delays for all the power states, and then we set the memory power state to prevent exposing any delays to the user. So we had to add some optimizations. Obviously, everything is not very simple. So we had to separate out the user and kernel information. So now we added time and memory references for both user and kernel. I'll explain in the results section why this has become important. Also, we realized that there was we should use a different power state for the user and different power state for the kernel. Again, the combination of both gives us better efficiency, energy efficiency. So that I'll explain that again. Also, we added in an early detect optimization. What happens is that when you constantly delay short task for a while, you have accumulated delays that can be exposed to a task that comes in, which is a longer running task. So we bump the power state for the task by checking every 100 milliseconds if the current task is violating the perception threshold or not. So let me quickly come to the methodology. So we have a trace-driven simulation. We tried to implement this directly into the memory controller, but we were a little unsuccessful. I can go offline and tell you exactly what the issues were, but so we have a 4 gigabyte DDR3, 4 ranks. We use 5 interactive applications. ABI Word, everybody has used that. It's a word processing application. Gnumeric, a spreadsheet application. Anjuta, it's an integrated development environment for C++. Raise your hands who uses Anjuta here. I don't know. OK. GIMP, an image processing application. Lives is an integrated video editing and playback application. And we use a memory benchmark called memtester, just intensively test the performance of the main memory. So the next thing we do is we compare our IAMEM against ODSR, which is a static on-demand self-refresh. So during the entire process execution, we keep the memory power state in self-refresh. Again, intuitively, we know that this is not going to work out very well, but we compare against that. Again, we have another static optimization, static memory management, power management scheme, which is called on-demand power down, ODPD. Do the same exact thing. We keep the memory in power down state, active power down state, in order throughout the entire execution of the process. And again, in this case, entire execution of the task. And again, we intuitively know that there's slight issues with that. PAVM, which is the state of the art, it's a dynamic power-aware virtual memory, which I spoke before. You keep only the ranks in the higher power states for the current running process, and you keep the rest of them all in lower power states. And we compare against Oracle, which we call the Oracle, which is the best power state fit within the allowed delay. So let me quickly then talk about the Oracle time distribution. Basically, what we realized was that some applications are dominated by short tasks, which we saw right in the beginning. ABI Word, Gnumeric, Anjuta, and GIMP have generally lower performance demand because most of their tasks require users to complete interactive operations like editing text and so on and so forth. Subsequently, user memory can stay in either self-refresh or pre-charged slow state for a majority of the time for the task execution. There are less system calls, therefore kernel memory has even lower performance, so we can we can keep them in self-refresh and pre-charge slow. Lives, on the other hand, works on video clips and has a significantly higher demand for kernel memory, and therefore we must keep the kernel memory in a higher power state. Memtester, lastly, has the most demand for memory both in kernel and user space. Therefore, we have to keep them in higher power state. The next thing I'm going to talk about is per task energy. This graph is averaged out to Oracle. And we clearly see that Oracle is the best combination of the delay and energy. It's meant to be that way. PAVM task is to guarantee performance, so it consumes about 187% more energy than Oracle. The other static approaches do not adapt and do not adapt very well and are inefficient. ODPD means low delays, therefore higher power state is used, and therefore consumes a lot more energy, and you can see that clearly here. ODSR, on the other hand, consumes way less energy, which means that it was not the right combination of delay and energy. We'll see that in the next graph that it causes a lot of delays. So IAMEM comes closest to Oracle in terms of this combination of delay and energy. In ABI Word Anjuta, we see that IAMEM yields as much as 69% improvement over PAVM. So now the other aspect of this is the task length. So again, here the average task length for all the tasks is normalized by Oracle, and we can clearly see that PAVM and ODPD provide high performance, but at the expense of energy. We saw that from the previous graph. The average task length is sorry, I forgot to mention that. This average task length is actually divided into two components, the transition time and processing time. The transition time is basically the time associated with the transition from a lower power state to a higher power state for memory before I/O can be done. The processing time is basically the average task length. We see ODSR incurs large transition delays like we showed before. Again, the combination is not good. IAMEM comes within 2% delay compared to Oracle, and it matches very well to the perception threshold and allowed delays. Lastly, I want to present just the total energy. So when we were doing the entire, when we collected the trace, there was the actual task length, and then there was idle time associated with that task right after the task was finished. So we thought we should have a metric that actually takes into account the entire trace. So we include the energy consumed during idle time in this graph, and we see here that Oracle matches IAMEM matches Oracle with less than 3% difference, and IAMEM consumes about 25% less for the interactive applications as compared to PAVM. So in conclusion, IAMEM clearly outperforms existing mechanisms in interactive environments. Energy savings are done during the process execution. There is negligible degradation in performance, and we have made no modifications to the application. So in the end, IAMEM reduces the power memory energy consumption by 16% as compared to PAVM. This is including this is with the total energy metric. Thank you. Either I was too good or I was too bad. All right, thank you. Okay, you will, okay.
So, since no one has questions. You said that there were some complications with, you used trace-driven simulation because there were some complications with implementing this on a real system.
Would you like me to,
Could you tell us a bit about that?
Sure, basically what we did was, what we tried to do was we tried to flip the exact register which tells the operating system to change the power state of memory. But what happened was it would go ahead and change it, and this is my explanation. This is what I think happened. The memory goes down to a lower power state, but then the memory controller tells the operating system that there is a fault, basically, and the operating system completely freezes. Basically, the memory controller should have waited for the power state, for the memory to come back to active power down, active standby, and then say that this memory is now available and get whatever it needed to get. I don't think that happens, and that's why it gets chopped off. There was another person I was talking to, and we spoke, and it was kind of the same thing that he mentioned. Thanks.
So I just have simple 2 questions.
Okay.
So does this work for the power consumption? Did you actually measure the power, or you kind of calculated power from the power traces?
So we wrote a memory power simulator, which actually, it basically was a state machine based memory power simulator. So it just calculates just the memory subsystem, how much memory that, how much power that. So we didn't measure it with I know what you're talking about. There was a previous paper where we measured it with by connecting something to the motherboard, but no, we didn't do that here.
Okay. And you said that you kind of controlled the power state of the memory according to the task, right?
Right.
So as far as I know, like controlling memory power state is not easy.
It's not.
Like how, may I ask, how did you do that?
I'm sorry?
May I ask, how did you do that?
We could not implement it in the real application, so we did it in as a state machine, basically. As a state machine memory power simulator.
Okay. Thank you.
Yeah, thanks.